Okay, welcome back to the second session of Contributed Talks. This session will go from 1 to 1:40. We have 2 talks. Each talk will be 15 minutes, and we will leave 4 to 5 minutes for questions. The first talk is by Leshinskaya with Sharon Thompson-Schill, titled Inferences about Uniqueness in Statistical Learning. Thank you, Anna.
Among the most classic results in psychology are the findings from Rescorla and Wagner on classical conditioning. So let's suppose this rat is faced with a cue, let's say this light bulb turning on and some cheese, which is an outcome. So under what conditions will the rat learn to predict the cheese on the basis of the light turning on? Turns out that this is largely governed by 2 quantities, in fact 2 conditional probabilities. The first one is the probability of the outcome given the cue. So that's these yellow shaded areas in these 2 little time graphs here. So that's the probability of seeing the cheese given that you've seen the light bulb. But it also depends on another quantity, which is the probability of the outcome in absence of the cue. So that's these pink shaded regions here. And so in the top, the cheese occurs quite often even in absence of the cue, whereas it doesn't in the bottom. Turns out learning is much better in this scenario here, indicating that rats and other animals really care about this factor down here, which I'm terming really broadly uniqueness. That is, we really care that the predictor is a unique predictor of the outcome. And so the difference between these quantities is termed delta P. This factor is captured in learning models that many of us are familiar with, including the Rescorla-Wagner learning rule, at least in certain circumstances. And it is captured in more sort of Bayesian versions, such as the Kalman filter. And I'll come back to these ideas later on. But why am I telling you about results from the 1970s? Well, it turns out that they raise some interesting questions with respect to newer learning paradigms that I think a lot of us care about, at least I care about, which is statistical learning. So in the visual case, statistical learning is a paradigm where participants are shown streams of continuous events in which there are regularities. So for example, the forest is always followed by the kitchen and then by the living room. And even though participants' task is usually an unrelated cover task, they do incidentally acquire these predictive relationships. So it's interesting because statistical learning paradigms do differ in a number of ways from prior paradigms that have been used to test this delta P idea. In particular, as I mentioned, it's spontaneous, so it's not guided by any kind of task instruction or reward. There's no explicit strategy here because there is no task. It's implicit, there's a very large number of stimuli, and the information that you get from these streams rapidly exceeds working memory capacity, nor is there any reason to think people are rehearsing any of these quantities. Presentation is continuous, there's no trial structure, there's no indication of what is a cue or an outcome. And so I think this creates a question regarding what quantity is actually learned in statistical learning scenarios. Is it delta P, or is it something simpler, perhaps a conditional probability or a joint probability without factoring in this difference? And there's reason to think both answers are plausible. Work by Sobel and Kirkham has shown that these uniqueness kinds of effects can be seen in paradigms that are a little bit more like statistical learning. They're kind of in between the classical conditioning kind of examples that I opened with and this one. But most models of statistical learning do not incorporate delta P as a factor. And other work suggests, or at least there's a strong debate about whether delta P might be computed in a sort of deliberative, strategic way rather than in an automatic, implicit sort of way. So we set out to test this by presenting participants with a more or less standard visual statistical learning task, which they're exposed to 2 different streams of visual stimuli for about 10 minutes each. Our stimuli are dynamical events. This is partly to make them a little bit more naturalistic, so things sort of happen continuously in a continuous fashion. But otherwise, it's largely a classical sort of statistical learning task. Underneath this stream of events, there are certain regularities. Specifically, we designate 2 events to be a cause and an effect, such that the cause is going to predict the effect. During exposure, the participants are doing a cover task. So every once in a while, we randomly replace the typical event with a visual alternate. So sometimes the bubbles might be pink rather than blue, and participants just have to detect these oddballs. So this is fully orthogonal to any of the statistics that we care about in terms of learning. As I mentioned, what we're really going to manipulate is delta p. So this is the transition probability matrix for the high delta p sequence. So here's event n and event n plus 1. So if you've just seen the cause, you're very likely to see the effect right after it. So that's the probability of the effect given the cause. That value is high. And what's also important, of course, is that the probability of the effect in absence of the cause is low. In other words, a high delta p. So this means that the effect doesn't follow any of the other events, basically ever. We also present another sequence in counterbalanced order with a low delta p. Here, importantly, the conditional probability between the cause and the effect is equally high. This is just one number off. I guarantee you this doesn't explain the findings. It's just a little bit of stochasticity in our materials. What's important is that the probability of the effect in absence of the cause or following all the other events, so following not the cause, is high. So the effect is going to happen more often. And just to point out, these are totally visually different events, so there shouldn't be interference between these. And just to point them out, plot them on the same slide, we have high delta P, low delta P conditions. Again, the thing that varies is only delta P, and of course, event frequency. So the effect is going to be more frequent, and that's part and parcel of the delta P manipulation. You could kind of think of it as saying that the conditional probability between the cue and outcome or cause and effect has to exceed what you would expect on the basis of the base rate of the effect. The other thing we control for is joint probability. So that is here the probability of seeing a cause and an effect in a two-trial chunk. So that's also called chunk frequency, and that is also equated between these conditions. So we're going to test learning with a forced choice test. This specifically probes participants' knowledge of what's more typical, the cause followed by the effect, versus the effect followed by the cause. The reason we test this is this equates for item frequency, so you can't make this judgment on the basis of whether the leaves or the bubbles themselves were individually more frequent. And importantly, there's always a right answer in this question. So regardless of which condition you're in, it's always right to choose this because under all statistical measures, this is more likely to happen. So if people are doing less than accurately, that means that they're doing something incorrect, it's therefore not strategic. What we found is that accuracy is affected by delta P. So in the high delta P condition, participants were highly accurate, more accurate than in the low delta P condition, suggested that they are really spontaneously computing the statistic. What you can note here as well is that in the low delta P condition, participants are actually below chance. They're systematically wrong. And this is actually a puzzle in our data. There is no obvious explanation for it, and I think it suggests that there are more complex things going on, and we're working on figuring out what those are. But in case you're concerned that our measure is a little bit weird, we actually have a convergent and even more perhaps interesting measure, which is noticing. So we ask participants at the very end whether they noticed that certain events followed each other more often than others, and they about a quarter of them did notice the correct pattern of events for one of the sequences. Very few noticed them for both, and predominantly the one that they noticed was the one in the high delta P sequence. So this suggests that delta P actually affected participants' tendency to notice or become aware of these regularities, which I think is really interesting. In conclusion, or at least interim conclusion for the moment, statistical learning seems to be best described by delta P rather than joint or conditional probabilities, suggesting there's actually quite substantial inferential complexity to what people are spontaneously computing in these tasks. It suggests that the uniqueness of a predictive relation might be an inherently important statistical quantity that the mind computes without incentive, and that this computation affects noticing rather than being the product of deliberation. In the last part, I just want to talk about what might be the simplest learning algorithm that we could use to account for these data. So not what's the best overall model of learning, but what is the simplest? What are the minimal assumptions that we have to make to explain it? And I brought up at the beginning that the Rescorla-Wagner learning algorithm, which is a basic error-driven learning algorithm, will asymptotically compute delta p in some circumstances, not all. We wanted to know if this was true here. So we adapted it to handle sequential input and to build a matrix of associative weights among all the events. So it basically computes a degree of anticipation, calculates an error, adjusts those weights. What we found is that although the model does learn the weights among cause and effect, it doesn't reflect the difference between the conditions. The weights are equally high between the cause and effect in the high and low delta p conditions. And this is because there's no way for this model to handle this trade-off of weights, that if other weights are high, that this weight should be kind of downplayed. And there's a really, really simple way to fix this, and one that I think is actually quite cognitively interpretable, which is a step of normalization. So here, all we do is we assume that all of the weights to an event, let's say the effect here, have to sum to 1 after each update step. And this means that the weights will naturally trade off since they all have to sum to 1. So if others are higher, the non-unique ones will get damped down, and so we do see this condition difference. And just to show you, across all settings of learning parameter, the normalized model captures the fact that the accuracy is higher for the high delta p than the low delta p condition. So this suggests that perhaps predictive learning is somehow normalized by the base rate of events. I think that's really important to think about. But I should also point out that the Kalman filter, which is a Bayesian version of the Rescorla-Wagner learning rule, also handles this well. So it will perform like the normalized model. And the reason is because it assumes that the weights are probabilities. Probabilities have to sum to 1, and it's by virtue of that that we get this effect. And so it's interesting to really think about whether people are representing associative weights or actually probabilities. I think there's reason to think the latter. In any case, to conclude, predictive learning, even when spontaneous and implicit, follows the uniqueness principle as captured by delta p. I think this finding is important for our models of statistical learning, for design of experiments, and for asking questions about the brain. So with that, I'd like to thank my students, my lab, and my advisor, Sharon, and to all of you guys for your attention.
Yeah, have you tried just doing softmax regression instead of Rescorla-Wagner? It seems like it would do the same thing. That's my first question.
Sorry, I haven't, but I would love to talk to you more about doing that.
Second question is, you controlled for joint probability, but it seemed like you didn't pit joint probability against delta p, right?
That's right.
So, you know, you can set up experiments where they're balanced. You know, one would strongly predict one outcome, and the other would strongly predict another, and then you could see, you know, which is stronger.
That's right. That's a great suggestion. I do plan to do that. One thing I'll point out is that in the low delta p condition, the joint probability was always higher between the right answer and the wrong answer, and people were not above chance. So they could have used that that option to be above chance, and they weren't doing so.
Okay, and one last thing. Sorry.
Sure.
In some experiments we did where the subjects had to learn the conditional probabilities of the situation, it would take like an hour of exposure, and I wonder if your results would change if they were trained longer.
It's a great question. I'll try and look into that for sure. Thank you.